So this topic is Gaussian mixture models, and we shall apply the EM algorithm to estimate the parameters of the Gaussian mixture model. So our motivating example is student heights. Now, so the observed variables are the heights, which I denote as X, and the hidden variable is the gender. So the gender is not known. F and M, female and male, are the two genders. That's hidden. The parameters of our model is consists of pi f, pi m, mu f, sigma f, mu m, sigma m, and the subscript f and m pertain to female and male respectively. And we assume Gaussian distributions. So the probability of height given female is this distribution, which is n mu f sigma f, and likewise probability of the height given male z equals male is equal to this Gaussian distribution n mu m sigma m. And we have a large sample of heights, and the proportions of men and women is pi f and pi m, and that's also unknown. Okay, so pi f is equal to probability of female, and pi m is the probability of male, such that pi f plus pi m should be equal to 1. And therefore, the heights follow this distribution. Px given theta, all the parameters, equals pi f times n mu f sigma f plus pi m times n mu m sigma m. So before we begin with our analysis, let's make a list of all the probabilities that we shall encounter, and I shall focus on the female, and for the male it's likewise. Now I have the condition given theta is ubiquitous, so just so that it doesn't divert our attention, I have colored it gray. So the probability of ZF, ZF is shorthand for Z equals female, so that's equal to pi f, the prior for female. Probability of X given female is this distribution n X given mu f sigma f, which is given by this expression here. Px comma Zf is the joint probability of X and Zf, which is the product Pzf times Px given Zf, which is equal to pi f times n X given mu f sigma f. P of X equals, from the sum of probabilities, Px comma Zf plus Px comma Zm, which is equal to pi f n X given mu f sigma f plus pi m n X comma mu m sigma m. The conditional probability P Zf given X, so probability of female given height, is from the conditional probability law. It's Px comma Zf joint probability divided by Px, which is equal to this. Numerator is pi f n X mu f sigma f in the numerator, and the denominator is this, which is Px, which is equal to this expression here, pi f n X mu f sigma f plus pi m and x given mu m sigma m. Let's explicitly write down the objective in a formal manner. We have observations of the random variable, which is the height xn, n equals 1, 2, up to uppercase n. So these are the samples that are provided. The hidden variable, which is an indicator variable, is z sub fn and z sub mn, which is shorthand for zn equals f and zn equals m, respectively. And we have to perform the max likelihood estimate to obtain the parameters of this model. So theta hat is the max likelihood estimate, which is argmax with respect to theta of the likelihood of all the samples x1, x2 until xn. So this is the joint probability. So that's equal to argmax of the log likelihood is log of the joint probabilities, which is product n of p xn given theta, which is equal to, since the product, if you take it outside the log, it becomes a summation. So this expression is equal to argmax of summation log p xn given theta, which is equal to, and substitute the expression for p xn given theta, which is equal to this log of pi f n xn given mu f sigma f plus pi m n xn given mu m sigma m. And this is not easy to maximize. Why? Because we have a log here, and each term here contains a Gaussian, which is an exponential. So that would be easy to take the log of each term. But since we have a summation of two exponentials, it's not easy to take the log and then take the derivative and find what's the maximum. Therefore, we have to use the EM algorithm for this problem. So the EM algorithm for our problem is as follows. The current iteration is theta superscript I is the iteration. And we have two steps. The E step involves finding the probabilities QIZ, which is P of Z given X theta I of hidden variable Z from X and theta I. So QIZ is the probability distribution of the hidden variable Z. The M step is to find the maximum of the expectation, conditional expectation, when Z follows the distribution Qi of Z of the log likelihood, log P x comma Z given theta, and that is the Q function Q theta comma theta I. So let's look at the E step specifically for our problem. The current iteration, theta I, we have all the parameters of the model, pi f I, pi mi, mu fi, sigma fi, mu mi, and sigma mi. The E step involves finding the probabilities Qi of Z, the probabilities of the hidden variable Z, which is P of Zn given Xn comma theta I. This probability, let's focus on only one sample Xn for now. So Pxn given theta I is equal to this expression pi fi n xn given mu fi sigma fi plus pi m I n xn given mu m I sigma mi. The joint probabilities Pxn comma Zf are given by these expressions. The first one is pi fi n xn given mu fi sigma fi, and likewise for pi m for the male. Therefore, the conditional probabilities of the hidden variable z's are given by these expressions here, and you can see why, because the denominator of this expression, let's focus on female, is equal to pxn, and the numerator is equal to pxn comma zf, and therefore the ratio of the numerator to denominator is p of zf given xn. And these conditional probabilities pzf and given xn theta I and pzm and given xn theta I are nothing but the qiz's, which is what we want for the E step. Therefore, we have devised our E step, which is explicitly carried out by using these expressions here. So now we are ready to implement the M step. The parameters from the current iteration are given, and from the E step, the distribution of the hidden variable z, which is qiz, is already determined, and that's determined for all n equals 1 through uppercase n. So for each sample xn, we find out the corresponding zn using the parameters theta I. Now the M step. So the M step, we have to maximize the expected value of the log of the joint probability pxz given theta, under which distribution when z follows this distribution qiz. And if you notice, I moved the subscript I to the superscript here because I need to make room for the subscript later on in this derivation. And so this expected value of log px comma z given theta is the q function q theta comma theta I. So q theta comma theta I is explicitly given by this expression here, expected value under z following the distribution qiz of summation n log pxn zn given theta. Why this summation now? Because we have different samples, and I skipped one step. It should have been a log of the product of the probabilities, and when you transfer the product outside the log, it becomes a sum, and that's equal to, I move the expectation inside the summation, so that becomes equal to summation n of the expected value of log p x n zn given theta, when z is following this distribution qi of z. And now what I'll do is, since this is an expectation of the z, I have z is a binary variable, either male or female, so I can get rid of the expectation sign by explicitly plugging in the values of z, the probabilities of z in each case. So I have summation n q fi of n log pi f p x n z f n theta. That's when z is female with this probability, and likewise the second term in this expression is when z is male, and we get this term here in each term of the summation. So this completes the derivation for the m step. The q function is explicitly given by this expression here, and since each of these probabilities pxn given zfn comma theta and pxn given zmn comma theta are the conditional probability distributions given female and given male respectively, so they are replaced by the n mu f sigma f and n mu m sigma m, which are the Gaussian distributions. And so this is what we have in the m step. The QFs are the known quantities, which I have colored in green, and the reds are the unknown, which I have colored in red. So this is the Q function for the m step, and I misspoke when I said we have completed the m step. What I meant was we have completed the derivation of the Q function for the m step, and now our goal is to maximize the Q function. How do we do the maximization? We take the derivative of the Q function with respect to the parameters theta and let it equal to 0. And this derivation is pretty long. I'll skip this derivation, but these are the variables. The pi f, pi m, and the mu f, sigma f, mu m, sigma f. These are, just as a reminder, the qf and qm's are known quantities. Anyway, so now proceeding with this derivation and letting it equal to 0, we get the values of the parameters. Mu f and mu m are given by these quantities. Sigma f square and sigma m square are given by these expressions, and likewise pi f and pi m. Take a look at the mu f and mu m first. So the numerator is this summation over all samples n, and we are summing xn, and we are applying the qfin as the weight. So this is the probability of z, the hidden variable, being female, and so these probabilities of the hidden variable being female are serving as the weights for the samples xn, and the denominator is simply the sum of the probabilities. So this makes sense. What we are doing is we are taking the average of the xn's weighted by the probabilities of each sample being female, and that gives us the average mu f. And mu m follows a very similar pattern. The expressions for sigma f square, which is the variance for the female distribution, that's again following a very similar pattern. So it's weighted by the probabilities of each sample being female, and then we have this usual expression for the variance, which is the average of xn minus mu f squared, and likewise for the variance of the male distribution. The pi f, which is the prior probability of female, is simply computed as the average of all the probabilities of the samples being female, which is summation of qfin divided by the total number of samples n, and likewise for pi m. So with the values of the parameters that maximize the Q function, we can now proceed and update all the parameters for the next iteration. And that completes the M step. So let's look at the M step. Oh, excuse me. Let's look at the complete algorithm. So this is the E step. In the E step, we obtain the values of the conditional distribution of Z, the hidden variable, using the existing values of the parameters and the samples. And then in the M step, we update the parameters for the next iteration. And we proceed like that for as many times as possible for a lot of iterations actually. EM algorithm is known to be quite slow, but eventually it will converge. So that's the EM algorithm for our specific problem. And we just had two Gaussians here, and we are now in a position to generalize to k number of Gaussians. So now let's generalize to Gaussian mixture models. So the PDF of the random variable x, which is a vector now, is equal to the sum of uppercase k different Gaussians, and the mixing coefficients are pi k, and each of these n given x, n x given mu k, sigma k is the Gaussian distribution, and the mixing coefficients are pi k, and the sum of all the pi k's, pi 1, pi 2, pi 3 until pi uppercase k should be equal to 1, and each pi k lies between 0 and 1 because these are probabilities of the Gaussians being active. And so each Gaussian is given by this expression. Now since x is a vector, mu is a vector too, and sigma now is the covariance matrix. So this is an example of a mixture of three Gaussians. So we have three Gaussians, 1, 2, and 3. Sorry, 1, 2, and 3, and they have different mu's, mu1, mu2, and mu3, and they also could have different sigmas. This one has a smaller sigma, it's narrow, and this one has a broad sigma because it looks a little broad, so it's got a higher sigma, and so on. And so this is a Gaussian mixture model with three Gaussians, and these heights are pi 1, pi 2, and pi 3, and they represent the probabilities of the corresponding Gaussians being active in generating one particular sample point. So the E step, this is the model, and our samples are indexed n equals 1 through uppercase n, and so the hidden variable zk tells you which Gaussian is active, and therefore summation zk is equal to 1, and so pi k is the probability of the Gaussian being active. So remember that zk is an indicator variable. So this is the E step. What we do is, this is our model, and I've written down the E step in a little different way, explicitly using for loops. So for each sample, and then for each kernel, that is for each Gaussian, we compute the Q, which is the conditional probability distribution of the hidden variables using this expression, and then we proceed with the M step, and so we update the mu k's, sigma k's, and pi k's in the M step. And so this is what like specific quantities in this example. So this is one sample xn, excuse me, I've used L instead of n, but this is xn, just like these, it's the same xn, and this is the first Gaussian. This Gaussian acquires a value of 0 here, so pi 1 n xn, that is for this particular xn, this is n xn given mu1 sigma 1, is almost 0. This is the second Gaussian here. And for the second Gaussian, at xn, this is xn, doesn't look like an n, but anyway, this is an xn, and this height here is pi 2 n xn given mu 2 sigma 2, and likewise this is pi 3 of pi 3 n xn mu 3 sigma 3. That's for the third Gaussian, this Gaussian. And the sum of these three give you the height of the this curve here, and that's summation k equals 1 through uppercase k is 3 now of pi k n xn mu k sigma k. With this we complete our Gaussian mixture model. End.